Hello Precalculus students, and welcome to a video on part 2 of mathematical models. So we're going to look at two more types of problems here. And the first one is similar to the second one. This is actually number 2. The first one that we looked at was looking at the distance between a point and a curve. And here we're also looking at a curve. So the first thing we actually want to do is get a little graph so we can get a visual of that curve. Now what we're asked for here is a right triangle has one of the three vertices on the graph of the curve, and that's at the variable location. And they're telling us which quadrant it's in at xy. Another is at the origin, and then a third point is on the positive x-axis at x0. And this x is going to be related to the x here, so they're going to be it's the same variable. So you'll see once we start to graph this. So the first thing I want to do is actually look at this equation. So this is a graph of a parabola that's opening down and translated up 16 units. So let's just graph that, a quick sketch of that parabola. So we know that this vertex right here would be up at 0, 16. Because it's got symmetry, right? It's not moved over to the left or to the right. And we do know that it's going to hit the x-axis, and we could easily figure out where it's going to hit the x-axis, but for this problem, it's not really important. All right, so we've got this parabola. And we can pick an arbitrary point when we want a point where x is greater than 0. So we don't want anything on the left side here. We want something over here. May as well pick it in the first quadrant. I'm going to pick it in the first quadrant. So there's our point, and that point is xy. But as we saw in the last example, we can also name that x, comma, 16 minus x squared. So another way of thinking of this point is x, 16 minus x squared, which is y. All right, so that's the ordered pair there with only x's now. We have just a single variable. So we've got one point there. Another is at the origin, so let's plot that point. And another is on the x-axis, so somewhere on the x-axis, where at x0. So the 0 just means it's on the x-axis, but the x means it's directly below the point that we chose. So it's going to be right here. That's x0. This is 0, 0. And the triangle that we're talking about is this triangle right here. It goes vertical, horizontal, and then it has that point right there. So this is the triangle that we're going to find the area of. So do we have the ingredients that we need to find the area of this triangle? And the answer is yes. It's a right triangle. We know the base. The base is just from 0 to x. So the base is x. And we know the height. The height is from 0 to y, which is 16 minus x squared. So the height is 16 minus x squared. So the area is 1/2 of the base times the height. All right, so let's write this down. So the area, 1/2 base times height, which is 1/2 of x times 16 minus x squared. And that is the area. We can improve this a little bit. That's the area as a function of x. This is 1/2. And we can just leave it, we can multiply it out. May as well multiply it out. So 16, 1/2. That's right. Let me do it in steps. Okay, 1/2 x, 16 minus x squared. And that would be a of x. Our final version now would be 8x minus 1/2 x to the third. And there it is, the area as a function of x. Okay, let's look at, and we could also maximize this the same way we've maximized others, but this is not a parabola, so actually we couldn't do it quite the same way. But we could check it and see if it's got a local max. We could record it. We could graph it and see if it's got a local max. Okay, let's look at the third example. So now let's read this. Okay, we've got An open box with a square base is made from a square piece of cardboard. So it's made from a square, 16 inches on the side, by cutting out the corners of the square. Okay, so let's draw what that looks like. So we have a square. And we're going to construct an open box. It's open at the top by folding up, by first cutting out some corners and then opening it up. So I'm just going to draw it like this. And then we'll draw. So I'm getting these square corners, but I'm also getting the leftover fold lines. So all of this is going to be cut out. This is going to be discarded. It's not going to be used for the box. And we're going to fold up the four sides. So we're going to get a little like a square box. Okay, and it is square because everything here is the same length. It starts out as a square and we cut out equal parts. Okay, let's see what it says. An open box is made from a square piece of cardboard 16 inches on a side. So the whole thing is 16. This whole thing is 16 inches. Okay, now we're looking for the volume, and we're cutting out x, right? So we're going to call this is going to be our variable right here. So this is x. All of these, because they're squares, they're all x by x squares. And when we take out the squares here, we're actually removing two x's from the 16. So the side length here is going to be 16 minus 2x by 16 minus 2x, because again, it is a square. So how do we find the volume of a box? Well, it's really a square prism, so the volume is going to be the area of the base times the height. Okay, that's the formula that we're going to use here to make things a little simple. So it's going to be the area of the base times the height. Okay? Well, the area of the base is 16 minus 2x by 16 minus 2x base. So this is 16 minus 2x squared. And the height is the thing that we're folding up. This is one of the sides, and they're all the same. They're all x. So times x. Okay? That's the volume as a function of x. Okay, so we can simplify this, but this time I'm going to leave it just like that. Okay, that's going to be it. So I'm just going to put the x in front so this dot doesn't confuse, because here I put an x like its multiplication here. So I'm just going to rewrite this as the volume as a function of x equals x times 16 minus 2x squared. Okay, so let's see what it says. So we've expressed the volume of the box as a function of the length of the sides cut out. Find the volume of a 2-inch square if a 2-inch square is cut out. So that means if x is 2 inches, so we're just going to find v of 2. 2 times 16 minus 2 times 2 squared. So the volume of that box would be 2 times 16 minus 4, that's 12, so 12 squared. That's 2 times 144. 2 times 144, which is 288. 288 what? Well, it's a volume, so they're inches cubed. Okay. Again, we might be able to maximize this. We just have to look at the function. We could look at it on a graph and see if it's something that has a local max. And we're not going to have to worry about that for this, but we could look at this a lot more closely, and you will, moving forward, you'll look at these problems in more depth. Okay, I hope you found this video helpful.